Okay, so here's the video to make up for the fact that I had to miss on Friday. Sorry about that, but sometimes things happen. Okay. So now that we have learned about the electric field, so again, just to remind ourselves, the electric field is equal to, technically, again, limits that the charge goes to zero of the force per unit charge. Or again, this limit portion here just simply means that we don't want the charge to be too big, so it doesn't back react. But if we ignore that part, basically what this thing says then is that what the electric field then is equal to the force per unit charge, which means, again, if we know the force, so again, if we know this, i.e. the force, we can then find the charge, or find the electric field, sorry. So this one basically says that if we have to know the force first, and then from the force, we can determine exactly what the electric field is. However, this works both ways. So basically what this one also says then is as long as we know the electric field, then we can simply multiply by the charge, and then that tells us what the force is. So all this thing says then is that, again, if we know the electric field, for example, by doing those integrals that we talked about in class, or if we had point charges, we could find the total electric field at a particular point, then we can simply multiply by the charge that we want to put at that point, and then that gives us then the force on that particle. So good. So all this means is what? We can work both ways. So if we know the electric field, we can easily find the force, but if we know the force, we can easily find the electric field. So either way that we want to do it works absolutely the same. So this is all we're going to concentrate on right now. So if we know the electric field, which again, we know from looking at point charges and from doing the integrals, whenever we have continuous charge distributions, we can then determine the force, and then from the force, we can find the acceleration. And again, as long as the acceleration is constant, we can then use our kinematic equations. So let's talk about an example. So let's see how this actually works. So for example, so let's say I have two sheets of charge. So here are my sheets of charge. And in this case, let's say, I don't know, for funsies, how do I want to do this? Let's say I have the positive on the bottom here. And then the negative is going to be on the top portion. So this is effectively what we call a parallel plate capacitor, but we haven't talked about these things yet, so I'm not going to worry too much about them. And let's say that these guys are separated by some distance here. And let's say I have some charged particle which has a mass of m and a charge of q, going to be moving inside of them with some initial velocity of v0. Okay. Now, let's say that when this guy moves in, this guy then is going to what? He's going to feel a force, right? So basically we can see that because if I move my charge here, so let's say it's here at this point in time, we know that we're going to have an electric field inside the plates or inside these sheets here. So my electric field then is going to point from the positive charge to the negative charge. And since this is a positive charge, then this guy's going to feel a force in the direction of the electric field, which means the electric force this guy's going to feel is in this direction. Now, because that's in that direction, that means this guy's going to result in an acceleration in this direction, which is going to push it upward, causing this guy ultimately then to not move in a straight line when it goes on the inside along the dashed line here, but in fact, it's going to feel an upward force, which means this guy is going to deflect, right? And we know it's parabolically going to because the position is dependent on time in a parabolic way whenever there's acceleration. So what I want to know is by the time it comes out of the plates here, what is the deflection amount y or delta y, right? So this is what I ultimately want to know. So good. So first things first, again, let's look at the forces on this guy. So let's go back to the sum of the forces. So let me put it in an arbitrary coordinate system. I'm going to call the upward portion the y, and then call the x portion to the right. So since this guy feels an acceleration in the y direction, it's also being deflected in the y direction. Let's look at the y direction. And let's look at the sum of the forces. So some of the forces say that the sum of the forces then in the y direction are going to be equal to the mass times the acceleration. And then what? Then the only force acting on in this direction is our electric force. So we have our electric force then is going to be equal then to what? The mass times the acceleration. And what else do we know? So we know then that what the force is the same thing as the charge times the electric field is then equal to the mass times the acceleration. So according to this, then our acceleration then is going to be the charge times the electric field divided then by the mass. Now, continuing working in the y direction, since we want to know the deflection, that means we're going to use our second kinematic equation, which then says that the y is equal to the initial y plus the initial velocity in the y direction times time plus 1/2 acceleration times time squared. And it's plus because, again, our positive y direction's in the same direction as our acceleration. Here, we can arbitrarily call this as our origin here. So meaning that our initial y position is equal to 0. Our initial velocity in the y is also going to be equal to 0 because the initial velocity is only in the horizontal direction, hence our x direction. So this says our deflection there is going to be equal to 1/2 the acceleration times time squared, where my acceleration is simply given by this guy. So plugging that in, this guy becomes 1/2 QE over m times time squared. So this means to find the amount that would deflected, all I need to know then is the amount of time it spends with inside of the plate. So I want to know how much time does it spend in here, right? What is the amount of time it spends between the plates? Well, to get that, all we have to do then is look at the x direction. So let's look at the x direction. So in the x direction, we know that what? Xn is equal to x initial, right? I could take the initial of the plate here as x0, which is my initial position, plus the initial velocity in the x direction, which is all the initial velocity times the time, plus the acceleration, but there is no acceleration, so I'm just going to add a 0, right? So my x initial, I'm just going to call simply 0. So what I know is that what? In this case, since there's no acceleration, then the position is simply the initial velocity times the time. So let's say that the length of the plates here is this length from here to here, which we're going to call simply capital L. So this is the length of my plates, or the length of my sheets. So the time it takes to go from one end to the other end is then simply going to be what? V0 times t, which means t then is going to be the same thing as the length divided by V0. So finally, plugging that in, what this tells me then is that what? The deflection is going to be 1/2 the charge times the electric field divided by the mass, all times then the length divided by the initial velocity squared. So this is the amount of deflection it's going to have in my y direction. Awesome. So let's do another one in the same vein, and then we'll do something else in a slightly different vein. So this one says that, what? Again, we're going to have our parallel plates here, or our 2 sheets of charge. So here's my 2 sheets. And in this case, we're told that the electric field points upward. So here's my electric field. I'll write down the magnitude of that guy in just a second. Our plates here are separated by a distance of d, and we're going to have some length to them. So let's say this has a length of L. And I'll put in numbers here in just a second. But let's say now we have a charged particle, which in this case is an electron, which is then going to enter the plates. So in this case, it's going to enter with an initial velocity of V0 and an angle of theta relative to my horizontal here, so to the bottom plates. And what I want to know then is what? So by the time it gets inside the plates, right? So let's say it's here. So since this guy is a negative charge, what this means then is that his electric force is going to be in the opposite direction of the electric field, unlike last time, which it was in the same direction because it was a positive charge. So what this means then is this guy is going to ultimately feel a force downward, which means it feels an acceleration downward, which means that this guy is going to end up coming in, and it's going to start to curve downward. So from here, we want to start asking some questions, or at least the problem asks some questions. So what we want to know then is the acceleration, i.e. is the force too small that this guy's going to come up and say hit the top plate somewhere over here? Or is it going to be too strong that it's going to do something like this and then hit the bottom plate? Or is it going to be just enough for this thing to come through? So basically, part A wants to know, will it hit the top or bottom plates? So in this case, I'm not giving any options to actually make it through and not hit anything. So it's going to hit either one or the other one. And then part B then says, wherever it hits, how far from the left does it hit? So basically meaning that how far here, if it hits here, for example, how far is this from the left side? Or if it hits here, right, how far is that, and et cetera. So this is what we want to know. Now let's start putting in some numbers here. So we're told that the magnitude of the electric field is 2 times 10 to the 5th newtons per coulomb. We know the charge in this case, Q, is equal to negative the fundamental charge. The distance here is 2 centimeters. And what else do we know? We know the length here is 10 centimeters. And we're also told that the angle is 45 degrees. And this is an electron. So we know mass in this case is going to be, what, 9.11 times 10 to the minus 31 kilograms. So good. So let's look at this guy. So this guy is basically going to be the same thing as last time, at least with the acceleration. So again, let's start off with the force. So we can say the sum of the forces then in the y direction. In this case, I'm going to take the similar axis. I'm going to call this my y-axis. This is my x-axis, so that my initial position in both directions, again, is simply going to be 0. Again, it's going to be equal to ma. The only force in this direction then, actually, I'm not going to take my positive to the right. I'm actually going to take it downward. So let's see. Yeah, let me take it downward. Actually, no, I'll keep it upward. That's fine. But for this part, I'm just going to call it y is downward, so that way I don't have to worry about the negative side. But anyways, so my force then in this case is simply, again, ma. Here we're going to get E then times E again is equal to ma, which means my acceleration, same thing as last time, is equal to the charge, which is the fundamental charge, times the electric field divided then by the mass. Again, this thing's technically pointing downward, but temporarily for this part of the problem, I'm taking downward as positive. Just so I don't have to worry about the negative sign. But when I put in my kinematic equations, I'll have to put it in as negative. So good. So similar to last time, but unsimilar to last time, is the fact that, again, we're going to work in our y direction. Y direction. And we're also going to work in our x direction. So I'm just going to go ahead and write both of them down. In the y direction, we're going to have y then is equal to y0, which again, we're going to call 0. So I'm going to have an initial velocity in the y minus 1/2 the acceleration times time squared, times time on here. Where again, now this time it has a initial velocity in the y direction. And then in the x direction, we're going to say x then is equal to our initial velocity x times time. All right. So let's think about what this thing is asking. So what it's asking is it going to hit the top plate or is it going to hit the bottom plate? So let's think about the top one first. What's going to be true? So what would be true then is what? If this thing keeps coming up, and let's say it wants to actually stop up here and then turn around and come back down, right? So one thing we can say is what? Let's find the maximum height that this thing is going to reach, y max, in then the vertical direction and see if that y max is then greater than the distance of d, which is the distance between the plates. Meaning that, again, if y max is greater than that distance d, then it's going to hit the top plate. But if y max is less than the distance d, then it's not going to hit the top plate. Then it's probably going to curl around and hit the bottom plate, right? Now, for that, we would need to know, for example, the time it takes to get the max height, and then plug that into the y expression then to find the time. Now, unlike last time, we used the fact that it went the entire length of the plates to then find the time it took for that thing to hit, or at least, come out. But in this case, we don't know exactly where it hit, so we can't use that it made it through the entire length. But what we do know is that by the time this thing reaches the top, it has to temporarily, momentarily stop, which means that all the velocity in this direction then must be only the initial velocity in the x. So the way we're going to then determine the time it takes to get the max height is to use the fact that the final velocity in the y direction must be equal to 0, which is then going to be equal to the initial velocity in the y minus the acceleration times the time to max height. So this tells me that t max height is then going to be equal to the initial velocity divided by simply the acceleration. Now, plugging that back into our previous kinematic equation. So now we can find y max and then simply being equal to the initial velocity into y times t max minus then 1/2 the acceleration times t max squared. Now let's plug in what t max is. So this is going to be the same thing as the initial velocity in the y direction squared divided by the acceleration minus 1/2. Now, when I square this guy, this acceleration here is going to go away. So I'm going to get a v initial y squared divided by the acceleration. But those two terms are exactly the same, except one is 1 minus 1/2, which means that this thing then is simply going to be equal to 1/2 the initial velocity in the y direction squared divided by the acceleration. So this is my height to the maximum heights. So in this case, if I plug in my numbers, what I find in this case then is that my maximum height turns out to be 2.56 centimeters. Now, again, if I compare that to my distance of 2 centimeters, we can see that 2.56 centimeters is greater than that of the 2 centimeters, which means that we have this scenario, which means it has to hit the top. So good. So now we can move on to the next part of the problem. So the next part of the problem again says, well, how far to the left does it hit, or how far from the left does it hit? So at what horizontal distance does it hit? So that's another way of asking the same question. So in this case, let's go back. So we know now that it's going to hit. So it's going to hit someplace like here, right? Well, now we know the y height at which it's going to hit. That's simply going to be that height of d. Okay. So all I'm going to do now is use, again, my y direction. We're going to substitute in that it's going to hit at the distance of d, use that then to find the time t hits, and then plug that back into the horizontal distance, then to find the horizontal distance at which it has. So let's do that. So now I can say then is that y is equal to d when it hits, which is then equal to the initial velocity in the y direction times t hit minus 1/2 a times t hit squared. So to make this look like a quadratic, I'm going to bring these two terms to the other side. So now what I'm going to get then is that 1/2 a t hit squared minus the initial velocity in the y direction t hit plus the height of d, sorry, that should be a d there, must be equal to 0. So now I've just got to solve a quadratic, right? So let's go ahead and do that. So remembering quadratic, we're then going to have that t hit is going to be the same thing as minus b, which is positive v0, plus or minus the square root of b squared. So that's the initial velocity in the y direction squared, minus 4 times a, which is 1/2 then of the acceleration, times then c, which is the height of the plates d, all then divided by 2 times a, so that's 2 times 1/2 of the acceleration. Good. So let's look at this guy. So this guy here is going to cancel him, which makes that simply a 2. Now, since here I have the negative sign, as we talked about last semester, that means that this term here is actually less than this term here. So this term is greater, which means both of these two pluses and minuses are actually valid solutions. Now, if we go back to our picture, though, what we can see is since this thing is parabolically moving, it would eventually pass that same height of d at the larger time as well as the lower time, which means we simply want to keep the negative sign. So let's use this negative sign here. So that means then our t hit, that in green, is going to be equal to the initial velocity minus the square root of the initial velocity in the y direction squared minus 2 times the acceleration times the distance d, all divided by the acceleration. So then we can say, well, x hit is going to be the same thing as the initial velocity in the x times t hit. Plugging all my numbers at this stage, what I find in this case then is the position at which it hits is going to be equal to 2.72 centimeters. So that means by the time this thing hits the plate, this total distance at which it has traveled is only a distance of 2.72 centimeters. Right? So basically a little more than a quarter of the way across the plates. So good. So let's do one more. Give another example. And this one, of course, is going to be one of my favorite ones because, again, it has to do with our favorite friend, harmonic oscillation. as you know, I love my harmonic oscillation. So what does this problem say? So this problem says that we're going to take our charged ring. So this is my charged ring where this guy has a total charge of Q. Okay, so here's my charged ring. And at the center of this guy is here. So this guy's going to have some radius of, say, capital R. And then we're going to confine an electron to move in between the plates of this guy. So basically, or at least across the center of this guy, I should probably say. So this is now my electron. So we know is that what? So our electric field for this guy, let me kind of write down what it is just to remind you. So we found in class by doing the integral that the electric field of the ring, I call it a disk, I mean a ring. So my electric field of the ring then is going to be Ke times the charge Q times Z, all then divided by Z squared plus the radius squared, all raised to the 3/2 power. Right? So this was our electric field. And in this case, this is going to point in the perpendicular direction to that of the ring, which I'm going to call the, again, Z direction. So it's going to be in the K hat direction. So what we can see then is that what? Again, for this ring, the electric field at the center of the ring is 0, which means my electron in this case is going to feel 0 charge. Now, as it moves upward, right, in this direction, the size of the force is going to get bigger because the size of the electric field is going to get bigger because of this term here, which means that it's going to feel more and more and more force downward until eventually it's going to stop, turn around, and then come accelerating back down until it reaches the center points here, where it has now, again, no electric field, which means the force there is 0. It's going to pass through, moving to the other side, where the force is going to increase, pulling it back to the center, because we know this is an electron, i.e. negative charge. This guy has a positive charge, so it's an attractive force, causing this guy to harmonically oscillate back and forth. So what? So we want to do in this problem is simply determine what is the angular frequency for this harmonic oscillation. So we want to know what is the angular frequency for the harmonic oscillation of this guy. So good. So again, we're just going to do a sum of our forces. So we can say the sum of the forces then in the Z direction are then going to be equal to the mass times the acceleration. Or again, in this case, it's just going to be the mass of the electron. Don't worry too much about that. So in this case, the only force acting on this then is the force of electric, right? In this case, we know our electric force is going to be pulling it back towards the center, which means our electric force is going to be in this direction, which is going to be the direction of the acceleration. So in this case, this will be our mass times the acceleration. And again, using that, this guy then is going to be equal to the charge, which is that of the electron. So it's going to be negative times the electric field of the ring is then simply equal to the mass times the acceleration. Fantastic. Now, since we want harmonic oscillation, we want to get in the form that A is equal to minus omega squared times some displacement, which in this case is going to be in the Z direction. Since we're working magnitudes here, let me drop that vector sign and write it this way. So now we want to rewrite my acceleration in this form. So let's do that. So now I'm going to get my acceleration then is going to be equal to negative the charge of the electron times the electric field of the ring, magnitude, divided by simply the mass. Now, let's plug the magnitude of this guy in here. So this is going to be then equal to minus E, which I'm going to move my K over. So I'm going to get a KE, QE, Z over Z squared plus R squared, all raised to the 3/2 power. Now, this is almost the right form. This is very similar to the last harmonic oscillator one that we did, where it's almost, so we have to kind of get rid of that Z in the bottom. And the way we're going to do that the same way we did last time, we're going to say that the distance Z is much, much less than the radius of this ring. So that in this case, the distance Z doesn't matter compared to the distance of R in the denominator, right? So basically all that means then is that this Z here, we can pretty much just ignore, just like we did last time. We don't effectively have to do a Taylor series expansion. I mean, we could if we wanted to, but we don't really have to. So plugging that in, so this means our acceleration then is going to be approximately equal to minus the electric constant times the charge of the ring times the charge of the electron, all divided by, did I forget my mass over here? I did forget the mass over here. I apologize. So there's my mass. Good. So let's plug that back in. So here I'm going to get simply an r squared raised to the 3/2 power, which is going to be an r cubed. So we're then going to get the mass of the electron times then the radius of the ring cubed, all then times z. Now, since this thing here matches now the same structure as this guy, we simply have to read off what omega squared is. So this tells me omega squared then is equal to the electric constant times the charge of the ring times the charge of the electron divided by the mass of the electron times then the radius of the ring cubed, or square rooting both sides. This then simply tells me that omega, or the angular frequency, is the square root of the electric constant times the charge of the ring times the charge of the electron divided by the mass of the electron times the charge of the ring cubed square root. So this is our angular frequency of the electron oscillating back and forth along the axis of this particular ring. So good. So again, all of this simply says that what? Again, going back, excuse me, that as long as, again, we know the electric field then will allow us to be able to find the force by simply multiplying by the charge times the electric field at that given point of interest. And then that allows us to find the force at that point of interest. So good. So next thing we're going to talk about is, it turns out that electric fields actually tell us a lot about conductors. So let's kind of talk about some conductors. So let's talk about what electric fields tell us about conductors. So let's remind ourselves, conductors are, again, metals where the electrons are free to move. So let's think about what these things actually tell us. So it tells us effectively actually three different things. So let's talk about this. So the first one says that what? If I had a conductor, let's say here's my conductor, and then I have this conductor here. And now what? Let's say I put a whole bunch of excess charges on the conductor. So let's say in this case, I'm going to put a whole bunch of positive charges inside of here, just for funsies, right? Now, even though it's only electrons that move, but as we talked about in class, we actually pretend that positive charges can move as well, but let's talk about it. So what's going to happen then is, now we know that what? The Coulomb's law says that we're going to get repulsive forces between all these positive charges, which means all these positive charges are going to get pushed away as far as they possibly can. Right? So basically what's going to happen then is that all these guys are going to feel repulsive forces, pushing them to the outside of it, which is the farthest they can actually move. So what's going to happen then is, when I put all these excess charges then onto the conductor, they're all simply going to move to the surface of the conductor. So this is the first thing we actually learned. So because of this, all of these charges, because of this Coulomb repulsion, all the charges are going to spread out as far as possible, but the furthest they can move from each other is to the boundary, which means that if I put this total charge of Q, then that means that what? All the charge then is going to be at the surface of then the conductor. So difference between a conductor and an insulator then is that an insulator can actually have charges uniformly distributed, but for a conductor, all charges will be on the surface. The charges will be on the surface. Now, the other interesting thing about this then is that because I get electric field lines, which all radiate around in all possible different directions, what happens then is that the superposition of all of these different electric fields means that the total electric field on the inside must be equal to 0. It has to be true. Now, the other way I can see that is what? If I had a whole bunch of charges on the inside, those guys would create an electric field, which means it would move, which it doesn't actually move. It just actually stays there. Okay? So that's the first thing we're going to learn. Second thing we're going to learn is that what? Let's say, again, I have a conductor. Here's my conductor. I'm going to have a hollow shell on the inside. So let's say I have a little cavity on the inside of there. And I'm going to put a charge on the inside. Let's say this thing has a total charge of Q, right? So let's think about what's actually going to happen here. So what happened then is this guy, again, is going to make electric field lines, which are going to point radially outward. from him. Beautiful. And let's say that the only charge I have is here, which means the charge of the conductor itself is equal to 0. So I have no charge on here. Now, what's going to happen is because the charges are freely to move inside of the conductor, what that means then is that what? All the negative charges inside the conductor are going to be free to move, which means they're going to move as close as they can to the positive charge, which means that I'm going to have positive charges on the surface of the conductor left over. It's going to do something like this. So basically, all the negative charges will be attracted then to the positive charge on the inside. But what that means then is if I look at the charge here, these charges, the negative charges, are going to shroud the positive charge, which means around here, my total charge then is going to be equal to 0 inside of this. But then on the outside, my total charge on the outside will be equal then to the charge. I'm going to put that as QO or Q out. It's going to be equal to the original charge, which is on the inside. So what's going to happen then is even though the actual charge is inside of the cavity, looking at it from the outside, I'm going to think that all the charge is actually on the surface of the conductor because, again, all the negative charges are going to be pulled to the inside to shroud that positive charge on the inside, which means only positive charges on the outside equal to the charge which is on the inside. So I'm going to think it's all actually on the outside, even though it's not. It's technically on the inside. Now, the other thing that's going to happen is notice that I'm also going to create a secondary electric field because I'm going to have what? Positive charges here pointing to the negative charges here, so that I'm going to have the electric field of the conductor pointing in the opposite direction as the electric field from the charge. Now, what's going to happen then is that the electric field of the conductor will be opposite to that of the electric field from the charge itself, but it's going to be equal in magnitude, which means that, in this case, my total electric field on the inside will simply be equal to 0. Okay? So what's going to happen is that my total electric field on the inside will still be equal to 0 in this case as well. Okay? So good. Now, the last thing is that it's going to tell us is that the electric field will actually be perpendicular to the surface. So how do I know that? Well, in this case, again, let's say I have charges all on the outside of this guy. So here are my charges. Great. And then let's say that I have components of my electric field which are parallel to the surface. So let's say my electric field is going to point something like this. Okay. So that means I'm going to have two components of my electric field. There's going to be the tangential part. Right. So this is E tangential. And then I'm also then going to have the perpendicular component of the electric field. We do that in green, I guess. So let's do it this way. So this is then my perpendicular component of my electric field. Great. Now, what's going to happen then is since my charges are free to move on the inside, this tangential portion of the electric field is then going to create a force, which means it's going to feel an acceleration, causing these guys to start to rotate about. So what's going to happen then is it's going to create a torque, and that torque is going to cause the charges on the inside to rotate about until eventually it's going to rearrange itself so that there's going to be no parallel portion or no tangential portion of the electric field, causing these guys to feel a force or a torque, which means that the torque will eventually go to 0, at which point I'll be having only the perpendicular components of the electric field. So that means, again, that in reality, my conductor then, here's my conductor, will only have electric field lines which point perpendicular to the surface. We cannot have any parallel portions of the electric field because in this case, again, they would create a torque, and that torque then would cause them to simply rearrange themselves until eventually they got to the points where they'd only be perpendicular to the field itself. So good. So these are the three things that we can learn. So again, we can learn that if there was any charge on there, they're going to redistribute themselves. So they're only found on the surface so that the net electric field will be equal to 0 on the inside. Now, this will be important for when we talk about things like Gauss's law, where again, since I'm inside, anytime I'm inside a conductor, then the electric field on the inside has to be equal to 0. And we'll talk about that again when we get to Gauss's law. Again, if I had a hollow cavity, then what's going to happen then is all my charges are going to rearrange. So that from the outside, I'm going to shroud the charge on the inside, but then the outside is going to look like that same amount of charge on the inside, but such that the total electric field on the interior, again, is going to be equal to 0. And then finally, the electric field has to be perpendicular to the surface. So last topic I'm going to start talking about here, but we'll have to finish this off on, what's that, Monday. So I'm going to introduce what's known as an electric dipole. So what's an electric dipole? So an electric dipole are two charges of equal charge where one of them is positive, the other one is negative. So for example, let's say this is positive, this guy then is negative, and then these guys are separated by some distance of d. So this is going to be my distance d, okay? So we're going to define what's known as the electric dipole moment, which then points from the negative charge to the positive charge in this direction. So this is what we call the electric dipole moment. So it points from the negative charge to the positive charge. Now notice that's in the opposite direction as the electric field. Remember, electric field points from the positive to the negative, where this guy points from the negative to the positive, where the magnitude of this electric dipole moment then is equal to what? So this is then equal to the charge of the positive charge times then the distance vector d. So basically what we're going to do is we're going to promote the distance between the two to a vector d, which then points from the negative charge again to the positive charge, where the magnitude of this guy is simply then equal to the distance between the two charges. Okay, so this is what we call the electric dipole moment. Let's talk about the units of this guy. So this guy is going to have units of what? Coulomb meters. So it's going to be our dipole moments. So what we're interested in is what happens if we put our dipole moments here into an electric field. So we want to put this guy into some sort of external electric field. So let's say that, for example, again, my dipole moment points in this direction. So it's my dipole moment. And let's say I have my negative charge here. So here's my negative Q, and then here's my positive Q. And let's put this in an external electric field where that electric field, say, points in the horizontal direction here. So that my dipole is oriented at an angle of theta relative to the electric field. So this is my electric field. So first thing I want to know is, what is the force on this guy? What's the net force? What's the sum of the forces on this guy? So F net. Will this guy actually feel a force? So let's find out. So what I know in this case then is that the positive charge is going to feel a force in the direction of the electric field. So it's going to be my electric force. And I'm going to call this the force on the positive particle. Simultaneously, my negative charge is going to feel a force on himself, but in the opposite direction, okay? Because he's a negative charge, so he's going to feel a force in the opposite direction. So this is let's call that F minus. Change my mind on that. There we go. So good. So what this thing says then is that since the two forces are in the same direction, so I'm going to call this my x direction. This says then the sum of the forces in the x direction are then going to be equal to F plus minus F minus. Okay. Awesome. Now, but from here though, since that's the distance d, right? This is my distance d. What we can see then is that what? Actually, I don't want to use that guy. I'll come back to you later. There we go. So we know then is that what? This is going to be the same thing then as the charge times the electric field, right? Minus then the magnitude of the charge, which is Q, times the electric field. But since the two charges are the same, the two electric fields are the same, so this thing feels no force. Right. So what does this mean? So this means then that this thing is not going to feel a force to accelerate it in one direction or another. Okay, so meaning that this thing's center of mass is not going to accelerate this way, and it's not going to accelerate this way. It is simply just going to stay in the same spot. But what is going to happen is, since the electric field is pulling on this guy to the right and this guy to the left, this thing is going to rotate about the center point, which means it is going to feel a torque. So this is where we're going to start off with on Monday then. Let's talk about the torque. on a dipole in an external electric field. So I can do some demonstrations there, but basically what's going to happen is, again, since one's being pulled in one direction, one's going to be pulled in the other direction, is it's going to want to rotate. So my dipole moment here, P, will basically rotate in this direction and this direction until eventually what's going to happen is that the dipole moment will align itself with the external electric field. We'll talk about why that's going to be true, okay, in class. But again, we'll pick up with here on Monday. But again, here's a video to kind of catch us up for the day that I had to miss. And yeah, make sure you watch this before you come into class, because we're going to pick up with this guy. And otherwise, I'll see everybody on Monday. Bye. There it is.